So let's say we have a vector valued function rt. Rt is a vector value. So rt gives a vector. So, and as t changes, the vector changes. So vector valued function, they define like a particular path. So if we have this curve defined by rt, and in this graph, there's also a vector field, capital F. Yeah, capital F. So vector field is like in every position of x, y, they define a particular vector. They can be in any direction. So what we want is this thing over here from curve C, going through curve C. Uh, the F dot tangent, actually, yeah, ds. So tangent is like unit tangent vector. Tangent is like when you're going through RT. Tangent is like a unit tangent vector is the change in RT. The tangent is the change in RT and it's a unit vector. So we are dividing it by this. And S over here is the like a piece of the curve. So curve is cut into many pieces. If those pieces was infinitely small, that's ds. So this integral is basically saying for each tiny piece, we multiply the vector field at that point with the tangent at that point, and we sum the multiplication for infinite points. So so for example, vector field at this point, let's say it's over here times the tangent. Then vector field at this point, let's say it's facing this direction times the tangent. This product for infinitely many points. So ds is like infinitely small. This is equal to, like, let's say rt, this over here. It goes in this direction. This is t is equal to a. It starts here. And then t is equal to b. It ends here. So we have a, b. So this is equal to f, the vector field at that position, times it by, you do a dot product with this dt. So this is how we calculate it. So this is a vector line integral. And then there is a conservative field. So conservative field is like if you have f, which is a vector field. Actually, let's start it differently. Quite difficult to explain it. So I took some gap. I took a long gap, and explaining it again would be quite difficult. So let's say I have a 3D surface. This 3D surface is defined by f, x, y. So this function over here is defined by f of x, y. And then it's differentiable everywhere. So at a particular point, we can find derivatives. Like let's say one pointing in the x direction, and one pointing in the y direction. So this surface is defined by f of xy, and then we have another thing called the gradient of f. It's just a white one. So gradient of f is partial derivative of f with respect to x in the I direction plus partial derivative of f with respect to y in the j direction. So this vector plus this vector gives the gradient of f. Gradient of f is the partial derivative of f of, uh, of f in the x direction. This vector and then this j vector f, a partial derivative of f in the y direction. The length of this vector is the partial derivative in the y direction, then the length of this vector is the partial derivative in the x direction. So this vector is parallel to the xy plane because there's only I and j, right? So I is like in this direction, j is like in this direction. These two vectors, they're parallel to this plane. So for the entire surface, we can define all of the gradient just in the xy plane. Since f is a function, there won't be like two values for a particular xy. So for every xy input, there will be a unique z output, right? So for every xy input, there will be a unique z output, and we can display the gradient of f in just the xy plane. So for example, this can be displayed over here. And then if we have a gradient over here, like much above, can still be displayed here. And suppose maybe at this point the gradient is decreasing. If the gradient is decreasing, then it would be negative. So negative in this direction, positive, positive, maybe in that direction. So I can like do this and then this. Wait, I need to check something. Hold on. All right. So where was I going with this? Yeah. This f sometimes he represented with a different function called the vector field function. A vector field function. So a vector field function gives like it's like defined by two equations, p of x y I and then q of x y j. A vector field function. This function just defines the vector field, like this one over here. So f of x y defines some vector field. So here, actually. Well, it's actually the sum of these. So it's actually one vector, but I'm representing them as two. So maybe negative, maybe it would be negative over here. Maybe components would be large over here, and so on. So a vector field, so this gradient of a function is also a vector field. A vector field is called conservative if there's a function that can be represented as its gradient. So if there is some function g and I can write gradient of g, let's say I make this g. G is a conservative vector field if there's a normal 3D function called g of xy where the gradient of g of xy equal to g. G is a conservative vector field if there is a if it's a gradient of some function, if I can represent it as a gradient of some function. Because some vector field, I can't represent them as a gradient of some function. They're just vector fields, but they are not gradient to any surface. Yeah, and if this thing is possible, if this is possible, then G is called the potential function of the vector field capital G. So we learned about conservative vector field. And there was a theorem, a fundamental theorem. Yeah. So this over here, this is a vector line gradient. So if F is a conservative vector field, then I can write like this of G times uh and then this. So the gradient of F, and then the fundamental theorem says that I take F at point B minus F point A, that this is equal to this. That's the thing I learned last. Oh, wait. Sorry. Not A and B. F of R, B, R, A. This is the fundamental theorem of line integrals.